Hi everyone. This lesson is 2.6 confidence intervals for proportions, and I'm continuing from where we left off in class. If you want to pause the video and read the problem, and then we'll work it out together. According to a study done by the Pew Research Center, 25% of teens are mostly internet users who say they mostly go online using their smartphone and not using some other device, such as a desktop or a laptop computer. The report states this percentage was based on a nationally representative phone survey of 802 teens ages 12 to 17. It was conducted between July 26th and September 30th of 2012. So is the 25% a p or a p hat in this problem? And the answer is it would be a p hat because it's based on 802 teens. P hat is your sample statistic, and this was based on a sample of 802 teens. So that's your sample statistic, sample proportion, and it's based on 802 teens. Do you think the true proportion P of all teens who are mostly internet users is also 25%? So as we know from discussing in class that every sample is different due to its natural variation, so not exactly, okay? It was a nationally representative sample, however. The sample proportion p hat is a single estimate of the population proportion, and we talked about this in class. That's called a point estimate. So our p hat value here as a decimal would just be 0.25, and n here is the sample size, and we know that they surveyed 802 teens. So right now, our best estimate for the true population parameter is p hat. So since we don't know that value, what we're going to do is make a 95% confidence interval and try to capture that true proportion. Okay, so in order to do that, we need to find the standard error. And if you'll recall, the standard error formula is p times 1 minus p over n. Since we don't know p, we're just going to substitute it with p hat. So we're going to do the square root of p hat times 1 minus p hat over n. So we know our p hat is 0.25. So we're going to do 0.25 times 1 minus 0.25 divided by n, which is 802, and then take the square root. And when you do that, you should get 0.0153. So that's my standard error. Okay, so again, if you think of the normal model, we would have 0.25 in the center, and then I would add 0.0153 to get the value to the right. That's one standard deviation above, and then I would subtract 0.0153 to get one standard deviation below. So to find the confidence interval, we need to take p hat plus or minus our margin of error. And since we're looking for a 95% confidence interval, we know that that's two standard errors on either side. So in order to find our confidence interval, we're going to do p hat plus or minus the margin of error, which is just 2 times the standard error. If we were looking at a 99.7% confidence interval, we would do 3 times the standard error. So here we have 0.25 plus or minus the margin of error. So the margin of error here is just going to be 2 times my standard error. And when I multiply that out, I get 0.0306 for my margin of error. So now we've just created this interval, and this is actually two problems, right? One of them is 0.25 minus 0.0306. And then my other one is going to be 0.25 plus 0.0306. And when you do that, you get the interval 0.2194 and 0.2806. So what that's telling me is that somewhere from 21.94% to 28.06% is the true proportion of teens who use mostly their cell phone. So in words, we would say we are 95% confident that the percentage of all teens who are cell mostly is between 22%, if I round up, and 28%. So if we were to have, let's say, 100 samples, 95 of them, approximately, should contain the true proportion of all teens that are cell mostly. Okay. Do you think it's likely that the percentage of all teens who are cell mostly internet users is as high as 1 in 3 teens? Well, 1 in 3 is 33.3 repeating percent, which is not in our interval. So I would say that it is not likely. Okay. You could look at the find a z-score and look to see if it would be unusual. But since it doesn't fall in our interval, we would say that it's not very likely. Okay, and please take a look at the summary. And if you need to, go back over the example we did in class. And then you also have the homework problems, which I strongly encourage you to do. And that's it. Okay, everyone, have a great rest of your day. So here's the value for z-scores that we wrote down earlier. And then here's some important facts. When the z-score is negative, it just means that that value is below the mean. If z is positive, it means that that value is above the mean. And when you get a z-score of 0, it just means that that value is equal to the mean. Let's next talk about normal distributions, which is a very important distribution in statistics. So the normal distribution is a model that we use that helps us to precisely describe where a value is in relation to the mean. And we can make a lot of estimations. We can calculate probabilities and percentages using the normal model. Most of you will have seen this normal model before. It's bell-shaped or it's a bell curve. And it's appropriate to use when modeling the behavior of distributions that are unimodal, which remember means one mode, and fairly symmetric. So we say fairly symmetric because in real life, there's not going to be a normal model that's completely perfectly symmetric where you can cut it in half down the middle and it's the same on both sides. Okay? We have lots of models in statistics, but this one particular type called the normal model is very useful because we can make a lot of estimations from this model if we know some clues. So we need to know values, we need to know the population mean, and we also need to know the population standard deviation sometimes. Other times we won't have it and we'll have to estimate using the sample standard deviation, but that's for another lesson. So here we have a normal model, okay, and it's representing the heights of randomly selected men. And if you were to take a large group of men and you were to create a histogram, it would come out to be bell-shaped. There's going to be a mode, okay, where most men are this certain height, and then you'll have men that will be taller and men that will be shorter, and men that will have an average height. So the average, as you can see, is right in the middle, okay? And that's mu, that's the population average. That's the average height of all males, which is telling me it's about 69 inches. And then it says the standard deviation is sigma equals 3. So if you take a look at these values, 69 falls right in the middle, okay? That's where mu will always go. And then 69 plus 3 gives me 72. That tells me that's one standard deviation above the mean. 72 plus 3 gives me 75. That tells me that that is 2 standard deviations above the mean. And 75 plus 3 is 78, which is 3 standard deviations above the mean. Okay, if I go backwards now, mu is 69, so 69 minus 3 gives me 66. So this is 1 standard deviation below the mean. So remember, we're going to put a negative there. 66 minus 3 is 63, so that's going to be 2 standard deviations below. And then 63 minus 60 is 63 minus 3 is 60, which is 3 standard deviations below. Okay, so what does this tell me? Well, I can make certain predictions knowing between what standard deviations any male's height would fall. So if you're a male that's 70 inches tall, I could approximate how many men would be taller than you or how many men are shorter than you. And we use this rule, it's called the empirical rule, which we'll talk about here shortly. What you should do now is pause the video and read about the following characteristics of the normal distribution. So here are some of the characteristics that you need to remember. The mean and the median are equal. So right here we have our mean, and that's also where the median is. And half of the values will fall above the mean and median, and half will fall below. The normal curve is bell-shaped and symmetric with respect to the mean. So if we were to fold down the center along the mean, it would be pretty much the same on either side. The area under the normal curve is 1 or 100%. So theoretically, this curve goes on forever towards positive infinity and negative infinity. Okay, but the area under it, the shaded area, would be 100%. The normal curve, as I said, extends endlessly in both directions. Okay, but as you can see, the closer you go towards positive infinity or negative infinity, the area gets smaller and smaller and smaller. And the normal curve changes its curvature from upward to downward and vice versa at 1 standard deviation below and above the mean. And these are called inflection points. So this value here is just whatever the mean is plus 1 standard deviation. So in our last example, it was 69 plus our standard deviations were 3. So 69 plus 3 gave us 72, and so on. A normal distribution is determined by its mean and standard deviation. Okay, so one normal distribution might have a mean of 23, like in this normal distribution, because that's the middle of distribution C, and a standard deviation of 1. It's 23 plus 1, 24 plus 1, 25 plus 1, and then we're at 3 standard deviations. Another distribution could have a mean of 15 and a standard deviation of 1.5. So I can tell here that the middle is 15, and I would add 1.5 to get to my other values. So normal curves can have many different values for the mean and the standard deviation. Fortunately, all normal distributions have the same relationship between the area and the number of standard deviations from the mean. So this is called the empirical rule. And what the empirical rule tells us is if a distribution is approximately normal, bell-shaped and unimodal, then that means that roughly 68% of the values will fall 1 standard deviation above and below the mean. Okay, so if you take into account male heights, I can say roughly that about 68% of male heights would fall 1 standard deviation above and below the mean. So if you go back to your diagram, 1 standard deviation above and below the mean would be here. So this tells me that 68% of males fall between 66 inches and 72 inches tall. And if I was to continue going out another standard deviation, 95% fall within 2 standard deviations of the mean, and even further out, 99.7% fall within 3 standard deviations of the mean. So that tells me that if I change colors here, 95% of males will fall between 63 inches and 75 inches tall, and since I can't fit it above, I'll put it here. 99.7% of males will fall 3 standard deviations above and below the mean. As you can see here, anything beyond 3, the area gets really, really small. So it's very unusual to have a male to have a height of more than 78 inches or less than 60 inches. Okay, it would be unusual or rare to see that. And pretty soon we'll be able to calculate those probabilities using either the empirical rule or using some other calculations that we can do using tables and the calculator. So you want to remember the empirical rule. It's really important. It's 68, 95, and 99.7%. And again, it just means that roughly 68% of the values will fall within 1 standard deviation of the mean. 95% of the values will fall within 2 standard deviations of the mean, and 99.7% will fall within 3 standard deviations of the mean. So something else that's important, as I was saying, the further out you go on the curve, the smaller the area gets. The empirical rule tells us that only about 5% of the values are more than 2 standard deviations from the mean. So if, in other words, what they're saying is, if this right here, this area, represents 95% of the values, we know that the curve is 100%. So if I do 100% minus 95%, I'm left with 5%. So the 5% represents this tail and the area under this tail. And of course, forever and ever, right? Because it goes on forever. So that would tell me that 5% of the male heights would be more than whatever that value was. I think it was 75. So more than 75 inches and less than 63 inches. Okay, so only 5% of individuals would fall into that category. So because of this, we say that values that are more than 2 standard deviations from the mean are unusual. And that's important. Okay, even more unusual beyond 3 standard deviations, but 2 is kind of the cutoff. So if you are more than 78 inches or less than, or no, it was, 78 inches or you're less than 72 inches, it would be very unusual. Okay, I think those were the values. I want to make sure. Yep, 78 and 63. Sorry, 75 and 63. So this is 75 inches and that's 63 inches. Okay, so any males more than 75 inches and less than 63 inches would be considered to have an unusual height, which just means it's rare to find that height. Okay, so many populations are approximately normal in their distribution. Let's go back again and look at the population of all men's heights. So we already kind of did that. We know that the mean went right in the center. That was 69 inches. So I'll do this again to make sure we're clear. Our mean is 69, and because the standard deviation sigma is 3, we're going to add 3 each time to get 1 standard deviation out. So 69 plus 3 gives us 72 inches, plus 3 is 75 inches, plus 3 is 78 inches. And then 69 minus 3 is 66 inches, minus 3 is 63 inches, and then minus 3 is 60 inches. So again, anything outside of the 95%, so anywhere this way or this way, is considered unusual or rare to find that a height of that size. Okay, so we have all our sketches. How do we find the actual percentages now? Okay, so we're gonna use our curve. So looking at the previous sketch and using the empirical rule, what percentage of men's heights will be between 66 and 72 inches? So we know that 66 is here and 72 is here, and they're both 1 standard deviation above and below the mean. So remember that 68%, it's kind of hard to see that, so let me write it like this. 68% falls within 1 standard deviation above and below the mean. So we can say that the percentage of men's heights that will be between 66 and 72 inches is 68%, approximately. Okay. 13 is saying, what is the probability that a man is between 66 and 72 inches? So the probability, remember, of an event is just the likelihood that that event will take place. Or in other words, the likelihood that a man will have a height between 66 and 72 inches divided by the possibility, the total possibility that they could. So our likelihood is 68% divided by the total, which would be 100% of all males. So that's just 68%. So when they ask you, and this is very important, when they ask you for what percentage and what probability, these are basically asking you the same exact questions. And that's very important to know because they're going to use those words interchangeably. Okay, the probability that a man is between 66 and 72 inches tall is the same thing as saying what is the percentage of men that will be between 66 and 72 inches tall. Okay, I'm going to let you all try numbers 14 and 15. And we kind of already labeled the diagram there for number 16. So let's work out some other problems here. And you all can answer number 17. Let's look at a new problem, number 18. So you'll want to pause the video and read the problem and then unpause it when you're ready. The speed limit on a road in town is 35 miles per hour, and a device used to measure the actual speed of cars traveling on the road finds the distribution of speeds to be approximately normal, with a mean of 35 and a standard deviation of 5. Answer the following questions using the empirical rule. So we want to label the normal curve below with the appropriate mean miles per hour and 3 standard deviations in either direction. Okay, and that's generally going to be the rule that we're going to follow for the remainder of the course. We want to, let's see, answer the following questions using the empirical rule. So we want to then, below that scale, label the speeds with the appropriate z-scores as you did in question 20. All right, so if we look at the problem, they tell us that we have a mean of 35 and a standard deviation of 5. So remember that this is actually mu and this is sigma. Okay, mu is, again, the population average or population mean. Okay, so you're taking into account all these cars whose speed was taken. So that's your population. And then we found the standard deviation as well. It was given to us in this problem. This is our population standard deviation of 5 miles per hour. Okay, so we know that the mean goes in the middle because it's the average. So 35 is going to go in the middle. And since my standard deviation is 5, I'm going to add 5 to 35 and I would get 40. And that represents 1 standard deviation above the mean. Okay, 35 minus 5 is 30. That would be 1 standard deviation below, and so on. Okay, I'm going to go back to the mean. 35 plus 5 gives us 40. 40 plus 5 is 45. 45 plus 5 is 50. So this is 2 standard deviations, 3 standard deviations. And if I go backwards, I'm just going to subtract 5 each time. So we know that this 25 miles per hour is 2 standard deviations below, and 20 miles per hour is 3 standard deviations below. So there's my normal distribution set up according to this problem. And by looking at it, I know that my mean is 35, and these are your z-scores. If you're a car that's traveling 40 miles per hour, right, you are 1 standard deviation above the average speed. Okay, so these represent the z-scores. Okay, so that would just mean z equals 1, and this means z equals -1. So if you're a car and you're traveling 30 miles per hour, you're actually 1 standard deviation below the average speed of the cars on that road. So then answering these questions, what is the probability that a randomly selected car on this road is traveling below 25 miles per hour? So think of this right here is our 25, and I'm going to put a little flag right here. We want the probability that any car randomly selected, right? So any car would have an equal chance of being chosen, that car is traveling below 25 miles per hour. So I need to use my empirical rule to figure that out. So if you'll recall, anywhere from 25 to 45 is 2 standard deviations above and below the mean. And using the empirical rule, we know that that area in between the two flags is 95%. So if I take 100% and subtract that 95%, it's going to leave me with this area and this area. So in other words, if I do 100 minus 95, I'm really subtracting away this piece right in here. So it's going to leave me with 5%, right? But that represents either side of the flag. We only care about this side. So I need to divide by 2 because remember, one of the properties of the normal distribution is that it's symmetric. It's the same on both sides. So these flags are the same distance from the center. So I'm just going to do 100% minus 95%, which gives me 5%. And then I'm going to have to make sure I take the 5 and divide by 2, which is 2.5%. So the probability that a randomly selected car is traveling below 25 miles per hour is actually just 2.5%. Now I want to know, what is the probability that a randomly selected car on this road is traveling between 35 and 40 miles per hour? Okay, so I'm going to take this this picture here, and I'm just going to copy paste. Okay, I'm going to shrink it down, and I'm going to, let's see if this will work. Let me put that back a second. Let's see. Okay, instead of redrawing, I can just go like this, and then maybe I can erase that stuff. Okay, so I'll do the best I can getting rid of this stuff. All right, I don't want to mess with it too much, but hopefully you can all see now. So now I'm looking for 35 and 40 and in between, right? So let me use a different color here. So 35 is here and 40 is here. And there's a couple ways you could do this, okay? So one way that stands out is, if you'll remember, between here and the furthest orange flag, so here, that's 68% of the data. It falls within one standard deviation. But I'm only looking for the probability that someone traveling on that road is going between 35 and 40 miles per hour. So using one of the characteristics of the normal model, I know that it's symmetric. So all I would have to do is divide this 68 by 2, because this area is the same as that area. And 68 divided by 2 is 34. So approximately 34% of cars traveling on that road will be traveling between 35 and 40 miles per hour. Okay, we know that the middle 95% of cars are going to be 2 standard deviations above and below the mean. So we know they're going to be between 25 and 45 miles per hour. And almost all of the cars on this road would be traveling between 20 and 50 miles per hour. Anything beyond those two values is extremely rare. In this book, we say anything above 2 standard deviations is rare. So the probability that someone is driving more than 45 miles per hour on that road would be rare. And the probability that someone is traveling less than 25 miles per hour would be rare. So if you think about it, anybody going above 50 or below 20 would be extremely rare. So mostly everybody, 99.7%, are traveling between 20 miles per hour and 50 miles per hour. The reason we can't say 100% is because remember, the whole curve represents 100%. So that's the end of this lesson. We're going to see more of the normal distribution throughout the entire book. So it's really important, this section, that you understand z-scores and also the normal distribution. So please go back over the notes and go over the summary here. These are highlighting the important things that you need to know. And then there's the homework at the end. This is the bare minimum of practice that you should do to feel comfortable with this section. If you need more practice, I can provide more problems for you to try. But doing these problems is, again, the bare minimum. If you've never seen this before and you need practice doing it, because a lot of what we're going to do going forward will relate to z-scores and the normal distribution, and your understanding of it is critical to understanding the rest of the course. So please reach out to me if you have any questions, and I hope you all enjoy the rest of your day.